Today we're going to finish up on chapter 13. It'll probably take us 10, maybe 15 minutes, and then we'll dive into chapter 14. So, last time I told you that cuprates were unique. They do unique things. They can react with acid chlorides and stop at the ketone. The other thing that they can do that's unique is conjugate addition to alpha-beta unsaturated carbonyl compounds. So I showed you an example of that, and I showed you some MO diagrams and also some resonance structures that show you how these alpha-beta unsaturated carbonyl compounds are reactive, electrophilic, electron poor, have partial positive charges at the carbonyl carbon and also the beta carbon. And so a nucleophile needs to decide where it's going to attack. In general, we have observed that organolithium reagents and Grignards prefer attacking the carbonyl carbon. There's a reason for that, but it's beyond the scope of the class. If you want to know more, come talk to me sometime and I'll tell you what I know, which is not much beyond what I just said. And we get 1,2 addition products from organolithiums and Grignards, just exactly what you would expect for attacking a ketone, tetrahedral intermediate, no good leaving group, wait until aqueous workup. It's called a 1,2 addition product because the nucleophile and the proton end up on atoms 1 and 2 of the carbonyl if you start counting at the oxygen. In contrast, the cuprate attacks the beta carbon. And I've showed you this product, which I've called a 1,4 addition product, though actually, if you look at the way we've drawn it, you might be tempted to ask, why don't we call that a 3,4 addition product? So I'll try to explain that briefly. I'll also show you the mechanism for a cuprate attacking an alpha-beta unsaturated carbonyl compound. Doing this, we can do this either from this resonance structure of the alpha-beta unsaturated carbonyl compound, or we can go from this resonance structure, which already has a negative charge on the carbonyl carbon, already has a pi bond between alpha carbon and carbonyl carbon, and already has a positive charge on the beta carbon. If we draw the resonance structure this way, then the cuprate simply delivers the carbanion equivalent to the positively charged beta carbon. We can draw that like this. That reaction just requires one arrow, and then we're done. Alternatively, then we're done with that step. Alternatively, if you want to draw the reaction from this resonance structure of the alpha-beta unsaturated carbonyl compound, you still deliver the R group to the beta carbon, but if you stop there, you'd have too many bonds to carbon. So we have to move the bond between alpha and beta carbons over to form a new pi bond between alpha and carbonyl carbon. And then we also have to break the pi bond between carbonyl carbon and oxygen and move those lone pairs out onto the oxygen. Either of those arrow pushing motifs is fine. Your product is this, your intermediate rather, after the addition of the cuprate. Looks like this, where we have a pi bond between carbonyl carbon and alpha carbon. Notice that the negatively charged oxygen, owing to the presence of the pi bond between carbonyl carbon and alpha carbon, you can draw a resonance structure where the negative charge from the oxygen is actually on the alpha carbon. So this is a resonance stabilized anion. It has a name. It's called an enolate for reasons that we'll discuss in a subsequent chapter. But you can see there's no good leaving group to be kicked off. Go ahead.
Did you start recording?
Did I start recording? Yes. Thank you for the reminder, though. Appreciate it. And actually, this is really important. I've often recorded lectures, and the audio is not recording. So when I upload it, you guys get to watch a bunch of silence. No, actually, when that happens, I either have to re-record or find last year's lecture and update it. But we're good to go today. We got the audio recording. Right, so this enolate structure, you'll notice, has a negative charge on the oxygen and on the alpha carbon. We're sort of stuck without a leaving group, and so there we wait until aqueous workup. Now, when we add water for aqueous workup, you can see there's two spots the proton could go on. Based on the product I showed you, where do you think the proton goes? Which oxygen or the alpha carbon? Yeah, I mean, if you look at the product, it's on the alpha carbon. That's actually where it ends up. That's not where it goes first. What I'm going to show you here is a detail you can forget about, but it will explain why this is called a 1,4 addition product. It turns out it is actually faster to protonate the enolate not on the carbon, but on the oxygen, for reasons that we don't need to get into. So it's actually really fast to first protonate on the oxygen to get this product. And this is where the name 1,4 addition product comes from. The proton ends up on the oxygen at position 1. The R group from the cuprate ends up on the beta carbon, position 4. However, and this product is actually called an enol. It's fast to protonate on that oxygen, but it's also reversible, because when you do aqueous workup and you steal a proton from water, you're left with hydroxide. So this actually can go backwards to the enolate, and it turns out that even though protonating on the alpha carbon is slower, the product that you get from protonating on the alpha carbon is actually more stable. So I'll draw that product for you here. Let's see, eraser. Here's the new bond with the cuprate. I don't know why I've continued to draw it red, but let's just be consistent. And then here's the hydrogen on now the alpha carbon. So ultimately, even though we formed the enol first, we pretty rapidly end up with the more stable isomer. The enol and the ketone, and so this is why we call it a 1,4 addition product, even though the hydrogen doesn't ultimately end up on position 4, okay? Minor detail, if you can feel free to forget about it, but it does give us an interesting chance to talk about something that's going to come up again in the class, and that is an enol versus a ketone. These are isomers. Look at them. They differ only in the location of the hydrogen and the pi bond. In the enol, the hydrogen's on the oxygen, the pi bond's between carbonyl carbon and alpha. In the ketone, the hydrogen's on alpha and the pi bond's between carbonyl carbon and the oxygen. The enol is more stable because carbon-oxygen pi bonds are significantly, and that's a long word to write out, significantly more stable than our carbon-carbon pi bonds. So the ketone is more stable. The enol and the ketone are in equilibrium. Even though we formed the enol fastest first, after a while of equilibrating, we quickly form 100% of the ketone. The process of converting between the enol and the ketone has a name in organic chemistry. It's related to the relationship between the enol and the ketone. This will come up again. But molecules that are isomers of each other that differ only in the location of a pi bond and a proton are called tautomers. So then we take the noun tautomer, we turn it into a verb, and the process of converting one tautomer into another is called, that verb is to tautomerize something. And then because we're not content with verbs, we nominalize that verb and turn it into tautomerization, which is multiple levels of English badness, but that is the process of converting the enol into the ketone. And you should understand that these are in equilibrium with each other, but the ketone is more stable. That's going to come up again. I think maybe if you took 351 and you learned about alkyne chemistry, when you did hydroboration and oxidation of alkynes, you got an enol product first, which tautomerized rapidly to a ketone or an aldehyde, I guess, depending on the alkyne. So, questions about that? Yeah.
So would the 1,4 product be the ketone?
Yes. Would the 1,4 product be the ketone or the enol? Technically the enol, but the enol converts to the ketone, and we don't bother making a distinction between the two. That ketone where the R group is on the beta carbon is the 1,4 product. Yes?
So should we always end up at the ketone?
Should you always end up at the ketone? Yes. Yeah.
Will there be any enol left, and if so, what percent?
Will there be any enol left? If so, what percent? Great question. You can do this in the lab and measure it, and I'm not sure what the equilibrium constant is. Usually in the lab, if something's less than 5%, we have a hard time observing it. So whenever somebody tells you this is the only product, what they mean is 95% or greater. Yeah?
So theoretically on an exam it says select all the
Ah, there it is. I'm just going to interject. Theoretically on an exam. Now you are all interested. Go ahead.
We just select ketone? Or
Yeah, you select all the products. It would be particularly dastardly for me to show both of these and expect you to choose only the ketone. So I'm not going to try to deceive you in that way. I could ask you, of these two, which is the major one? That seems like a decent question. Okay, others? Right, so one question that came up before class that I feel like is, you're going to need some practice on that, actually, by the way. So go ahead and practice alpha-beta unsaturation, addition of cuprates to alpha-beta unsaturated carbonyl compounds. We don't have a lot of more time for it. Somebody asked a question before class that I feel like is worth addressing, which is, what about this one and a cuprate? Maybe let's put an R group there. And the student said, isn't this alpha-beta unsaturated? And I said, yes, it is, but there's you remember that concept I mentioned last time that we were going to talk about later? Benzene rings have a special kind of property called aromaticity where they are very stable. Notice that in the reaction of a cuprate with an alpha-beta unsaturated carbonyl compound, the pi bond goes away. It's not there in the product. If we did this kind of reaction to a benzene ring, we would lose one of the pi bonds of the ring. That would destroy aromaticity for reasons that are not obvious to you now, but will be someday soon. And that's really unstable. So benzene rings are not reactive as acceptors of cuprates in these kinds of reactions. All right, that's sort of a minor point, but I thought I'd address it real quickly. All right, last concept in chapter 13 that we really need to deal with is an important concept for practical synthetic chemistry in the lab. So here is a molecule, and it's a ketone, but it's got an alcohol. And I want to do addition of a nucleophile to the ketone. And let's just say I want to use phenyllithium, which is just the benzene ring attached to lithium. And I'm hoping that after aqueous workup, my product is this. Except I find it doesn't work. If I try to do this reaction, the thing that I actually see is this. Hold on there. I thought that organolithiums react with ketones. What happened? Well, remember that organolithiums and Grignards and cuprates are all, in addition to being nucleophiles, are all really strong bases. The reason you know that, just draw, remember we've been taught to think of the organolithium as though it were a carbanion, where they're not air quotes when you write them down, are they? We're thinking of it as a carbanion, but if you want to know how reactive that is, how unstable it is, simply look up the pKa of the conjugate acid, and it's in the 40s. So this is a strongly basic reagent. And here you have hanging out, unbeknownst to the casual observer of organic chemistry, a proton whose pKa is 16. So what actually happens here is the organolithium reagent removes a proton from the acidic alcohol group. You end up with the conjugate base, which is the alkoxide, and benzene. If you wanted to make benzene, you shouldn't. You should just buy it. It's cheaper that way. This is a terribly expensive way to make benzene. And then, of course, you do your aqueous workup and you get your alcohol. That's not the desired product. The basic problem here is the acidity of that alcohol interferes with the basicity of your nucleophile and interferes with the reaction. So the strategy organic chemists have developed is we're going to do something to the OH group to convert it into something that no longer has an acidic proton. And the strategy is called using a protecting group. We don't have a lot of time to talk about this. We won't talk about the development of the whole strategy or what other alternatives there might have been or why the strategy I'm going to present you is a good one. In general, though, a protecting group lacks the problematic feature of whatever you're trying to mask. So for us, that's going to be it lacks the problematic acidity of the OH group. Second is it has to be easy to install. And by easy to install, I mean the reaction has to be fast and it has to be basically 100% yield. And then third, when you're done, it has to be easy, that's not a word, easy to remove. I was looking at fast while writing easy. Easy to remove, again, meaning fast and 100% yield. So the strategy that we'll use for our alcohol. Oh, and I guess the other thing we could write for, but I'm not going to write it down, is it can't interfere with any of the other functional groups in the molecule. So one strategy that works is the strategy of using a silyl ether protecting group. So here is the protection step. It's going to use silicon, which you might think, when have we ever seen silicon before? Silicon is highly abundant on Earth. It is one row down in the periodic table from carbon. So like carbon, silicon is bonded to 4 things. Here is the reagent, 2 methyl groups, and then a tert butyl group attached to silicon. Silicon's quite a bit bigger than carbon, and bonds between carbon and silicon and other atoms are a little bit longer than our bonds between carbon and other atoms. So silicon doesn't suffer from the same steric hindrance problems that carbon has. So if you were comparing silicon to carbon, you'd say this looks kind of like a tertiary alkyl halide, where you've got a chloro leaving group. This reagent, because it's a pain to draw, we abbreviate it as TBDMS chloride, where TB stands for tert butyl, DM is dimethyl, S is silyl, and then chloride. TBDMS chloride is the reagent, and then you need sort of a weak base because ultimately we need to lose the proton on the oxygen. So the base of choice is, I'm not sure your text even actually draws this for you. I certainly don't care for you to memorize this structure of this molecule. It's called imidazole, and it's just a weak base that isn't going to do anything else. I won't show you the mechanism of this reaction. It's not important in the text, and it won't really be important for us. But basically, we have the oxygen attack the silicon to make a carbon-silicon bond. Oxygen-silicon bond. Those are all very strong. An oxygen-silicon bond is quite strong, so that's the driving force for the reaction. And you need the imidazole to remove the proton from the oxygen afterwards. What we've done is we've converted the alcohol into something that we'll call a silyl ether. And it's like a carbon ether, only one of the 2 atoms attached to the oxygen is a silicon. It lacks the acidic hydrogen, so you can go ahead now and do whatever reaction you want to on the ketone, and the acidic proton is not going to get in the way. If you don't like drawing out structures, it turns out that neither do organic chemists for protecting groups, and so they like to abbreviate them with acronyms. So it's totally fine to abbreviate what I've just drawn there. Then you could do your nucleophilic attack of phenyllithium followed by aqueous workup. That would give you your tertiary alcohol over here. And then I'm just going to abbreviate the TBDMS group. The fact that I've not shown dashes or wedges communicates I get both stereochemical configurations there. And then lastly, we need to talk about the deprotection reaction. And it turns out that even though oxygen-silicon bonds are strong, fluoride-silicon bonds are stronger, in part because fluorine's more electronegative than oxygen. So people have found that if you use fluoride, F-, as a nucleophile, you can kick the oxygen off the silicon through a substitution reaction. Again, the mechanism of that isn't important. It won't be important for us in the class. Of course, you have to have a counter ion, and it would help if the counter ion would help the fluoride ion to be soluble in organic solvent. So a common choice is what's called a quaternary ammonium ion, 1, 2, 3, 4, where we have 4 alkyl groups attached to the ammonia. That's tetrabutyl ammonium fluoride, or TBAF for short. I'm not going to write out tetrabutyl ammonium fluoride. Somebody's about to raise their hand asking, do we need to memorize the structure of tetrabutyl ammonium fluoride? Don't bother. You can if you want. I mean, more power to you, but I assume you have other things to pay attention to. So tetrabutyl ammonium fluoride, I'm trying to move this over, sorry, will remove the silyl ether and restore the alcohol in its place. That's the deprotection step. And again, the reason this works is because the protection and deprotection steps are both fast and 100% yielding. And that allows you to sidestep the whole problem with the alcohol. You'll want to practice that. We don't have time to go into it in detail right now. You'll want to practice that into some practice problems, recognizing when you're going to need a protecting group by paying attention to potentially undesired side reactions of acidic protons on alcohols with your organometallic reagents. Okay, other questions about that? Yes?
And you can't just rip off the hydrogen from the alcohol and do whatever you want, because is that just too reactive?
So yeah, the question is, why couldn't I just, once I get here, could I add a whole other equivalent of phenyllithium and really push the reaction forward? I don't know. My guess is that doesn't work so good because of electron-electron repulsion. Now your molecule's negatively charged and you're coming in with something else that's negatively charged. So it's an interesting idea. I don't know that somebody's probably tried it and it didn't work well, but I don't know. What else? Yeah?
Can you explain the purpose of imidazole again?
Imidazole is just a weak base. If you look at what's missing from my starting material to the product there, where did the proton go? Imidazole removed it. I mean, if you want, I can draw the conjugate acid of imidazole, make it stop. The imidazolium ion, that's where the proton from the alcohol goes. Yeah, what else? Yeah?
When I was looking at that, my initial thought was do a reaction that turns alcohol into chloride, and then
Okay.
do your reaction with phenyllithium, and then do some more reactions with chloride back to alcohol.
Okay, so an alternative strategy might be, could we turn this into something else that's not a silyl ether? You mentioned the chloride. That's not a bad idea, though I would be worried about this strong base doing an E2 elimination reaction with the resulting alkyl chloride. All right, so we got to jump to chapter 14. Yes, go ahead.
You mentioned a lot of things that we don't need to memorize. What do we need to memorize?
Everything else, except for the things I know. That's a tough question to answer comprehensively in 30 seconds. So in the past little bit, details that we've had to memorize, there's not really any first principles that we know right now or that I've taught you that are going to teach you why cuprates can react with acid chlorides and stop at the ketones. So probably got to memorize that. There's also not any good first principles details I can teach you so far to tell you why organolithiums and Grignards do 1,2 addition with alpha beta unsaturated carbonyl compounds, whereas cuprates do conjugate addition at the beta carbon. So that's a memorized detail. Probably you have to memorize or at least be familiar enough with these reagents so you can pick them out of a lineup if I ask you to predict products or provide reagents for a process. And you ought to know how to do the protection and deprotection reactions. You don't have to memorize structures. You don't have to know mechanisms here. That was longer than 30 seconds, so I failed. Also, I am 10 minutes longer than, I told you 15 minutes on this subject, and we took 25. That is okay. Should I speak faster? You're like, scribble, fast. Yeah. Slow it down. All right. So, chapter 14 is going to involve aldehydes and ketones, and we're going to do addition reactions. Why? Because aldehydes and ketones don't have a good leaving group on them. And, yeah.
I had a question. This is section 10 of chapter 13.
Yes.
Which of the reactions from last year synthesis?
So in the synthesis questions in the chapter 13 problem set, or even at the end of chapter 13, the question is, which reactions do I have to know from 351? Only those which are useful in those problems. Perfect. This is a question that I get all the time for folks that it's been a while since they took 351, maybe over the summer, maybe you served a mission in between 351. There's a handout on the content page of Learning Suite, or there should be, I'll check and make sure it's there, that summarizes the 351 reactions. It's not worth a lot of your time now to go back and read frantically 351 chapters, but if you look at that handout, you can review reactions and reagents that were available to you previously. It's good to be able to use them in a synthesis, and you're probably going to have to pick them up on the fly and forgive yourself for not remembering them, but also allow yourself to take time to remind yourself what they are and use them. Yeah. Okay. Chapter 14. So we're going to start out with a simple addition reaction. It's not a particularly useful one other than it illustrates the basic concept of an addition reaction. So here is an aldehyde, and we're going to use CN- as a nucleophile. And your text also uses HCl. Note that do not run into the lab and try this. CN- and HCl make HCN, and HCN smells like almonds, and if you can smell them, you're probably already dead. So actually, when people do this in the lab, they don't use HCl, but I'm sticking with the conditions that your text uses. No, your text is not actually trying to kill you. And yes, before you go in the lab and try a reaction, do some research and figure out how people actually do the reaction. CN- is its conjugate acid, as I said, is HCN, and it's very dangerous, but the pKa is around 9. So our sort of comparison point is, can the nucleophile attack directly, or do we need to protonate first? And we've usually said, yeah, if it's as strong enough of a nucleophile, if it's as reactive or more reactive than a negatively charged oxygen, probably it can attack directly. If it's less reactive than a negatively charged oxygen, probably you need some help with acid catalysis. That's probably what's going on here with the HCl. I'm going to show something slightly different from your text. I will promise you not to ask you about it. Only it's not that hard, and you're going to have harder questions, so I don't feel bad not asking you about it. Probably what happens here, your text shows CN- attacking directly to give a negatively charged intermediate, which then gets protonated. But HCl is a strong acid and probably isn't going to wait around for a negatively charged oxygen to form. Probably what you've got here is sort of general acid catalysis where the Cn- attacks the carbonyl carbon at the same time as the pi bond is breaking, and as negative charge is building up on the carbonyl carbon, we pick up a proton from HCl that's in solution. And we get this product. We would have called it a tetrahedral intermediate, only there's no good leaving groups on it anymore. And this is the final product. It is called a cyanohydrin because you've added cyanide and hydrogen to this aldehyde. And we'll come back to what you can do with this, maybe in a subsequent chapter on nitriles. Just as a preview, if you use strongly acidic aqueous conditions and heat, organic chemists like to draw a triangle for heat. I'm not sure why, but if it helps you, you can draw little flames to help you remember that it's a fire or it's hot. That will hydrolyze the nitrile. If we can draw out the structure of the nitrile, which is a triple bond between carbon and nitrogen, strongly acidic aqueous conditions can actually hydrolyze the nitrile to a carboxylic acid. And and that's a useful functional group. There may be some synthesis problems you face later on, especially after we cover nitriles that do this. That's cyanohydrin formation. Again, I promise not to ask you about this mechanism. I do expect you to be able to predict the product for cyanohydrin formation, and it's the same thing for aldehydes or ketones. Yeah?
Can you go backwards this reaction with a base?
Could you go backwards for this reaction with a base? Great question, and the answer is absolutely. Yep. All you got to do is deprotonate the oxygen, and then you can kick off Cn- as a leaving group. It's probably another reason why they're using HCl to prevent that backwards reaction. Okay, that's sort of boring, so I want to spend some more time on an interesting reaction. This is interesting in biology and food science. It's involved in vision. It's involved in diabetes, and that's reactions of amines as nucleophiles with aldehydes and ketones. So there are a couple of variations on this, but they follow the same basic pattern. Let's start with an aldehyde, which we can just put an R group there and be general. The reaction involves, let's start now with a primary amine. A primary amine is going to be something where there's an R group attached to a nitrogen and you've got NH2, only one R group on the nitrogen. And it turns out for this reaction you need an acid catalyst. Sometimes in the text we'll abbreviate that as HA, but if you're in the lab you actually have to decide which one. So good options here include acetic acid, which is organic soluble. Also a favorite one, not favorite one from 351, para-toluene sulfonic acid, or TSOH. What is that? Okay, fine, if you want to see it. This should be bringing you a little bit of PTSD. Thank you. That was the appropriate response to that joke. This is para-toluene sulfonic acid. It's basically an organic soluble version of sulfuric acid. Often, to make this process happen, you need to, I'm going to put in parentheses, remove water. I'm going to show you as we draw the mechanism that water is a byproduct of this reaction. And sometimes in the lab, to make it happen, you need a strategy for removing water, because all of the steps of this reaction are equilibrium steps. They can go backwards versus forwards. The product replaces the oxygen with the nitrogen, and you end up with this product, which is called an imine. And then, of course, water is your byproduct, and your acid catalyst is reformed. You have to be real precise with your pronunciation of amines and imines. Nobody says amines. I guess maybe the Brits say amines. I'm not sure. But in America, we typically use our favorite favorite vowel, which is the schwa, or amine, right? But it's imine, right? So someday when you're teaching your children what I sounds like, when it makes a short sound, imine. I is for imine. I dare you. Somebody write a children's book. I is for imine. This is sometimes called in biology and biochemistry a Schiff base. And this reaction in your text is called imine formation, because you're forming the imine. That's really creative. But for food scientists out there, this is actually the first step in a reaction you know as the Maillard reaction. When you read a recipe and it says stick that dough into the oven and bake it until it's nice and what? Golden brown are the key words. That's how you tell the Maillard reaction has happened. And it's actually quite complicated, but the first step is often reaction of amines, which are present a lot in the proteins that are involved in food, with aldehydes. Where does the aldehyde come from? Sugar. Glucose is an aldehyde, and so we'll say more about that in a little bit. So that's imine formation. A related reaction, and I'll show you the mechanism of this for a minute, but let's just take a general overview. To show this reaction, I actually need to draw the structure of an aldehyde or a ketone. So let's let it be this aldehyde, and let's use a secondary amine instead of a primary amine. So here is an amine with two R groups attached. Okay, that is a secondary amine versus a primary amine. Again, we'll use an acid catalyst with the same sort of choice as above. And again, we'll probably need to remove water for this to happen efficiently. Turns out the product of this reaction is not an imine. It still has the nitrogen in place of the oxygen, but instead, the pi bond isn't between what used to be the carbonyl carbon and the nitrogen. It's between the carbonyl carbon and the alpha carbon. This is called an enamine. And I think people drop the E after ene. Ene is for alkene. I usually like to put it there because otherwise people say enamine, and that sounds like an enema, which is a procedure that you may do as a physician on some of your patients, but it's not intended to be anything here. So enamine with a long E. Enamine. With fronds like these, who needs anemones? All right. Nobody knows that one. That one was from Finding Nemo. We saw Finding Nemo in the theater with my 2-week-old son in 2003. So that's how old I am. All right. So there's some differences. You can see some selectivity differences depending on the structure of your amine. Go ahead. Yeah, sorry, thank you for that. The aldehyde, the H should still be there. Yeah. Thank you for that correction. It's still an aldehyde. What else? Okay, let's do mechanism. And then hopefully we can talk some biology. We'll do the mechanism of the first one. For enamine formation. We'll try to be as general as possible. I'm going to show you what organic chemists think happens. As I've tried to tell you, the issue of whether you can attack the carbonyl directly or whether you need some help with an acid catalyst is an important one. It's one that in general your text glosses over. I do want you to know this mechanism as I'm showing it to you, okay? The evidence is that the first step is general acid catalyzed. That means the addition step of the amine attacking the carbonyl carbon, breaking the pi bond, happens at the same time as the carbonyl carbon picking up a proton. There's some pretty good evidence for this in my grad level OChem textbook. So I imagine you're okay accepting that on faith. You don't want me to bust that one out and start reading from it. But all right, so that's an equilibrium step, meaning we could just as easily go backwards at this point. The backward step would involve lone pair electrons on the oxygen acting as kicker-offer to kick off this ammonium ion as a neutral amine, as the amine leaving group, okay? But if instead we regenerate our acid catalyst by having the conjugate base of our acid remove a proton from that ammonium group, that will generate an intermediate, which is found in your text. You have the carbonyl carbon, what used to be the carbonyl carbon, now attached to an oxygen and a nitrogen. That intermediate, just as a reference point, is called in your text a carbonyl amine. All right, so the presence of the acid catalyst expands the possibilities of what can happen next, because we can use, when we've been at tetrahedral intermediates before, we've looked for good leaving groups, and if we didn't have one, we were sort of stuck. The acid catalyst can trade who's the good leaving group. Notice I told you we could go backwards because the ammonium ion is a good enough leaving group as the neutral amine for the oxygen to kick it off. Now it's not. The acid catalyst stopped this from being a good leaving group. But the acid catalyst, if it protonates the OH group on the carbonylamine, can convert it from a neutral OH to this positively charged oxonium ion, which now is a good leaving group. So here's the good leaving group. Now you have lone pairs on the nitrogen. Now the nitrogen is the kicker offer. And lone pair electrons kick down and kick off water as the leaving group. I told you I would show you in this mechanism where water leaves, and we would talk about why you want to remove water. So let's draw the products of that reaction. Here's the water that left. And what's left behind is the nitrogen that's doubly bonded to what used to be the carbonyl carbon. And the nitrogen is bonded to two things, well, the alkyl group and a hydrogen. And then the nitrogen has to have a positive formal charge. This intermediate is called an iminium ion. It's the conjugate acid of an imine. And if you want to pull this reaction towards the imine product, it's a good idea to have some strategy like distillation or something else for soaking up the water and removing it from the reaction. Why do I say that? Because at this point, water is a good enough nucleophile to come in and attack the carbonyl carbon of the iminium ion, and that would just be the backward step to get you to this intermediate. But if we're removing water, that will slow down that backwards reaction, and then we can use the conjugate base of our acid to remove the proton from the iminium ion, and that will get us to the imine product. And our acid catalyst is restored. Okay? So that's imine formation. Key principles are nitrogen can attack the aldehyde, but you have to protonate the carbonyl oxygen at the same time. From that point on, the next three steps are using the next two steps are using the acid catalyst to trade around who's a good leaving group. We deprotonated the nitrogen, then we protonated the oxygen, then water, then the oxygen became a good leaving group. It was kicked off by the nitrogen to give us the iminium ion, And then at that stage, removing that proton gave us the imine product. Yeah?
When we're drawing, hypothetically for the test, when we're drawing these reactions, we need to make sure we have reversible errors before basically drawing.
Okay, so if you were drawing a mechanism and you were going to be evaluated on it on a test, now we're interested. I saw a bunch of heads pop up. Sorry. How would you have to show equilibrium arrows? I've never been that picky myself, nor do I think any of my colleagues are. Also understand my tests are actually multiple choice. So actually what you have to do on my tests is I show you a bunch of mechanistic steps and I say, which of these is wrong? Or which of these is right? You still, it's not actually any easier. It may be more difficult. For example, let me show you something that would be wrong. How's that? Let's start with that carbanolamine. An example of something that is wrong would be the neutral carbanolamine, and I show you something like this. Kick off that. Why is that bad? Because OH minus is a bad leaving group, right? Good. That's an example, all right? That may be on there, so just pay attention. Okay, other questions? Yeah? I think so, yes.
So what's the backward step to go from right before the water leaves to get back to the carbonyl?
The backward step to get to the carbanolamine?
Yes. What's that?
Yeah. Maybe we should talk through all of them quickly. Let me show you how to do that. While I'm setting that up, I saw another hand over here. Yes? No?
Yes, I was wondering why the acid, there we go, why the acid coordinates the OH when like with pKa values.
Right.
be preferred for the
Okay, so the question is about this step. If you look at the carbanolamine, the oxonium and its two potential adjacent neighbors in this mechanism, the pKa of this oxonium ion should be around -2. The pKa of this ammonium ion should be around 11. So it's actually more stable to be here than it is to be here. It's better to have the nitrogen protonated than the oxygen. So how is it that this is possible? Again, if you should think of it as a landscape where we're ascending a peak at this stage to come to a high plateau, and there's peaks and valleys in there, and one of them is lower than the other, but then on the other side of it we go downhill again. So you're right that there's probably more of this ammonium ion than this oxonium ion, but if we're removing water to push the equilibrium forward, then it's no problem. We're still going to get the imine product. Okay, let's talk briefly about how to think backwards through a reaction like this. It turns out that the mechanism arrows, when you want to draw reverse of imine formation, the reverse is called imine hydrolysis. How you do that involves exactly the same intermediates, you just draw the arrows differently. And I usually tell people go home and do it, and they get confused and sad. So I thought this time around I would actually get you started on it. So let's start on the last step, imine and the acid. Look where we were before. How do you think I get from imine and acid to iminium ion? Which means I draw an arrow from where to where? From the lone pair on the nitrogen to the H of the acid. Okay. And then you confirm, do those arrows actually lead to the intermediates shown? Looks pretty good. Okay. Now iminium ion we'll just, since we're talking about it this way, oxonium ion. What do we got to do there? We have to add water. Okay, so that means lone pairs on water attack the carbonyl carbon of the imine. This step actually teaches you something that you maybe didn't know. Imines are electrophiles in much the same way that aldehydes are electrophiles. They have an electrophilic carbonyl carbon. So we attack the carbonyl carbon, break the pi bond. That gets us to the oxonium ion. Okay, you are part of the way there. Before next time, finish this off. Finish here. Okay. All right, see you next time.